We spent the better part of Chapter 3 worrying about how to graph quadratic equations and determine certain points associated with them. And in this final section, we're going to graph quadratic inequalities, when we're going to have less than or greater than symbols, or less than or equal to or greater than or equal to. We will do so with both two variables and one variable. And the steps that they have for us for two variables include, first of all, graphing the parabola, and then determining whether we should have a dotted or solid graph for the parabola, and then to test a point to see whether we should shade on the inside or the outside. So let's look at some examples to see how we could do these specifically. In example 1, we're asked to graph a quadratic inequality in two variables. So we take a look, y is greater than x squared minus 3x minus 28. And the first thing that I would consider is, in standard form, don't we already know that 0, negative 28 is a point on our graph? And I'd also take the time to take a look at that trinomial and realize that it factors. And so that tells us that our x-intercepts are going to be at negative 4 and positive 7. We also know that we're going to graph this thing as a parabola because it was x squared. Also, the directions told us it was quadratic, so that makes sense. And should it be dashed or should it be solid? Well, since it's strictly a greater than symbol, not equal, we're going to want this thing to be a dotted line. So you can see we have our x-intercepts, we have our y-intercept. And step 2 said to take a point inside the parabola. I don't know that we always need to take something inside, but we should take something that's pretty easy to work with. So we're going to take a point that's not on the parabola, and we're going to test it. So if we take 0, 0 as just an example, plug it into our original inequality, we would say that 0 is greater than 0 squared minus 3 times 0 minus 28. Or 0 is greater than 0 minus 28, or finally 0 is greater than negative 28. That's true. If that's true, then that means that purple point, the origin, is part of our solution. And so in step 3, we're asked to shade. And since the origin is part of our solution, then we want to shade it and everything inside the parabola with it. Example 2 is borrowed straight from our textbook, using a quadratic inequality to model some real-life situations. We're told that a rope is used for rappelling down cliffs, and it can support a weight in pounds provided that W is less than or equal to 1480 d squared, where d is the diameter of the rope in inches. So it should make sense that the larger the diameter of the rope, the more weight it can hold. So can we graph and interpret this information? So the first thing that we want to do is graph the parabola, and remember our question would be, do we want to make it solid or dotted? Look at our inequality symbol. It's less than or equal to, and because of the equal, we want to make it a solid line. We want the full parabola, not dotted. Next, we're going to test a point to determine how we're going to shade. So since we know the parabola is going to be a solid line, it doesn't benefit us to pick a point on the parabola, so we're going to pick one not on the parabola. Our authors chose to use the point 1, 3000. If you can see that basically we're looking at something that's going to pass through the origin, a rope with 0 diameter can hold 0 weight. Basically, just about anything above the origin, if we chose 0, 1, 0, 3, they went over 1 unit and went up 3000. That's going to be inside the parabola. And when we take a look at this, we find out 3000 is less than or equal to 1480 times 1 squared. That's not true. 3000 is greater than 1480. And so when we choose the point that's inside the parabola, it doesn't work. And so we're going to want to shade on the other side. We're going to want to shade below the parabola. And you can see the image that our authors have given to us. They want us to interpret this, and the idea would be that we would like to be in the blue region because as our values are going out to the right, the diameter of the rope is getting thicker and thicker and thicker, and so we can hold more and more weight. That's why the parabola is going upward. It would be dangerous to try to lift something that's 3,000 pounds with a rope that only has a diameter of 1 inch. However, if you choose some other point, like look where 3,000 is for W and come down beneath, if we had a 1-inch diameter but only 500 pounds, we probably would be safe. We would be in the blue region. Now in example 3, it's our challenge to graph a system of quadratic inequalities. In the last section we were doing nonlinear systems where we just had parabolas and lines, or two parabolas, parabola and a circle intersecting. Now we're going to do that with shading as well. So we have two inequalities here, f of x and g of x. They're both parabolas. You can tell that because of the x squared. You can tell that there's a greater than symbol, there's a less than or equal to symbol. One is oriented upward, one downward. So let's look at f of x first, and realizing that we're in standard form, a first question we might ask is where's the y-intercept? If we have -4 for a constant, then this function should be passing the y-axis at 0, -4. Things don't always factor, but looking at this trinomial, it seems like we could say x plus 4 and x minus 1, and that would lead us to finding out our x-intercepts. So we have a pretty good sense of at least 3 points now. We can start to find the vertex, we can find the axis of symmetry, but we're going to use a little bit of technology to graph this as well. Is our parabola going to be dotted or solid? Well, let's look back at the inequality symbol. Look, it was a strictly greater than, so we don't want it to be equal to. Our parabola is acting as a boundary, but not part of the solution, so we want that to be dotted. So taking a look, here is our parabola. It's dotted. And then in terms of shading, we can pick any point, and our authors suggested we go inside the parabola. You can go inside or outside, it doesn't matter. But I would suggest picking an easy point, and because the origin 0, 0 is on the inside, I think that's a good thing to choose. But you can also, you can check that out. Is 0 greater than x squared plus 3x minus 4 when you plug in 0 for x as well? You're going to get 0 is greater than -4, so that's true. And so we would want to shade on the inside, but here's just a quick little hint. If we set up our function so that it's f of x is either greater than or less than whatever the inequality happens to be, and then everything else is over on the right, if it's a greater than symbol, we should shade above. If it's less than, we should shade below. So there's a picture of our inequality for f of x. Now turning our attention over to g of x, we want to do the same thing again, and we want to find a couple of points to help us graph. I think the constant 6 at the end tells us that we're going to have 0, 6 for a y-intercept. And the -1/2 here are a little bit onerous, but if we factor them out, look how nice that trinomial becomes. X squared plus x minus 12, that factors into x plus 4 and x minus 3, and so that tells us that we have 2 more x-intercepts for our second parabola. It's coincidental, perhaps, that the -4 happens to be a point shared with both. And then dotted or solid, well, we go back up to our inequality for g of x and see not only is it a less than symbol, but there's also the equal sign underneath. And so for that reason, we want this boundary to be part of the solution, and we make it solid. So there is our graph. And just coincidentally again, going inside, that does include the origin. You could choose 0, -5, you could choose -1, +1. All of those points are inside the green parabola. If you want to check to see if those points are true, plug in those values for x and y and see if your inequality holds. If you want to go to the outside and check to see if it's false, go ahead. But something else to consider, if you have the ability to say g of x and put all of the rest of the expression over on the other side, on the right, if your symbol includes a less than, then you're going to shade below that graph. And so here are our two intersecting, overlapping inequalities. And the solution set are going to be all of the points that are inside the two areas. So if we can look at those areas in there, it would include any of these points going up along the green parabola, but we could get infinitely close to the dotted orange boundary, but we wouldn't want to touch those. Anything that is purely orange or purely green is not part of the solution. It's what's orange and green together. In example 4, we're asked to solve a quadratic inequality in one variable, both algebraically and graphically. When we look at part A, we see the trinomial 2x squared minus 3x minus 20. It's a quadratic, we see the x squared, and we want to know when is this expression greater than 0. It might help us if we try to factor it, but the 2 and the negative 20 and the negative 3 all make for a lot of guesswork, so the AC method is a fairly good way to approach this. We get 2 times negative 20 because we look at our A and our C values and we come up with a product of negative 40. Then we ask the question, are there any factors of negative 40 that add to give us negative 3? The negative 3, remember, comes from the B value. So we look at some possibilities. We have negative 40 and 1, negative 20 and 2, negative 10 and 4, and negative 8 and 5. And it looks like that last combination is both going to multiply to give us negative 40 and add to give us negative 3. So we can rewrite that trinomial as a 4-termed polynomial. And now we can try to factor this by grouping. We do so, and we hope to take out things so that we can be left with a set of parentheses that are identical. If we take 2x out of the first and second terms, we're left with x minus 4. And if we take a 5 out of the third and the fourth terms, we're also left with x minus 4. That's beautiful because that means we can group together and get 2x plus 5, and x minus 4 is greater than 0. For the moment, I want to hold off on the inequality and just solve to find out where the zeros are. So I use the zero product property and say 2x plus 5 equals 0, and also x minus 4 equals 0. On the left, if we subtract 5 and divide by 2, we should get negative 5 halves, or negative 2.5. And on the right, if we add 4, we come to x equals negative 4. Looking up at the timeline, or the number line over on the top right, what we have done is we've found the zeros at negative 2.5 and positive 4. But remember, our inequality is strictly greater than. We don't want these values, so they are our boundaries. They're open circles. It creates for us 3 intervals, from negative infinity up to negative 2.5, from negative 2.5 to 4, and from 4 to infinity. And we would want to test these things out. So in the first, on the far left, I chose x to be negative 10, and I plugged negative 10 in wherever I saw x. So I came up with 200 plus 30 minus 20, and that's something positive. That's greater than 0. That's good. I want that. In between negative 2.5 and 5, I just chose 0, and so we would get negative 20 is less than 0. We're looking for a greater than symbol, so I don't want to include that. And on the right of x equaling 4, I chose x to be 6, and I came up with 72 minus 18 minus 20, and I know that that's going to be a true statement. I don't even have to finish it out. I just know that my left-hand side is a positive value that's greater than 0, and that's true. So we're going to have these two rays as our solution, and if we are to write this in interval notation, we would say that we want all of the values of x from negative infinity all the way up to negative 2.5, and that U symbol in between is a union symbol, it means that we also could want from 4 to infinity. So it's an either-or situation, and we put parentheses around both the negative 2.5 and the 4 because we don't want to include them as part of our solution. Finally, in part B, if we wanted to solve this graphically, we know where our zeros are, we know how it's graphed, and I changed my view a little bit here. I shrunk it vertically just so that we could see things relatively nicely. You can see how the graph of the parabola goes. It's a dotted parabola because we are having a strict inequality. And if we want things that are greater than 0, then we want the times when the function is above the x-axis. And so although you don't see very much of it, it's all of the values between negative infinity to negative 2.5 and from 4 to infinity. If we included the middle, you would see that that's when the parabola is below the x-axis, or that's to say, that's when the y values are negative. So we don't want those. Just to wrap things up here a little bit, we're only talking about solutions to inequalities when they satisfy both of the inequalities. So when you see the graph over on the left here, if you can find the points such as negative 2, 4, which is only shaded blue, that's not a solution to the system. If you can see a red point that's not blue, maybe 1, negative 5, that's not part of the solution. We only want to have the purple, where the blue and the red come together to form purple, like the origin, like negative 1, 0, like negative 1, negative 1. Those points are part of the solution. And for that matter, we can't include where the two parabolas themselves, the blue and the red, intersect, because if you notice, the red is dotted. The red parabola is not part of the solution, even though the blue is. Thank you for watching. We'll post your homework. Please ask us if you have any questions.